This is Algebra 1, Term 3, Lesson 10. Today we will do some exponential applications. We'll begin in slides with some growth decay questions, including some questions from GeoGebra. Then we'll move over to Desmos Classroom to do a few application problems and a few transformation questions as well. They will be introduced to exponential regression equations. And then finally we'll come back to slides and students will have an opportunity to create their own exponential growth function and their own exponential decay function. So let's start with our slides. So first we're given an equation of a function that represents the balance in so they're being asked what do these numbers represent and what is the growth factor and what is the percent rate of increase. Now those are not the same. The growth factor is the multiplier, which is the 1.03 in the equation, but the percent rate of increase is actually just 3%. We're doing the same thing on the next slide, but this time we're doing decay. So it's not decreasing 85%, it is decreasing 15%. Because we started 100%, what percent is it decreased from 100%? And that would be 15%. So the multiplier is 0.85, but the percent rate of decrease is just 15%. And how are those related? Well, you could always start with the 100% and ask how far away is it from 100%? Is it going up or is it going down? So that's how we determine our percent rate of decrease. Now once you've done that, you can decide if you want to go over to Desmos or continue in your slides. I would probably continue in the slides because you're practicing these same concepts each slide. So here's the scenario. This was given in GeoGebra, so they'll click the link and go find this same question. And then they will answer the questions in GeoGebra and insert screenshots of their work. My suggestion to the kids is make their window really tiny when they take their screenshots and then cram all that work into a small space, and it makes it really easy to cut and paste into their slides. So let's take a look at the GeoGebra. So this is GeoGebra, illustrative math specifically, and these are some practice questions. So here's the problem, here's the equation, and these are the questions related to it. So right here they can type their answers, and the beauty of this is they do have an equation editor. They can click on this pi here if they need to type any kind of mathematical expression. Just makes it a lot easier than dealing with slides. So if they will type that in here and answer the questions and then go down to the next one, how quickly is this flu spreading? What can you tell from the equation? What does f of 1 and what does it mean? What is f of 3.5? So we're practicing our function notation and we're also interpreting a exponential function in a context. Now we go back to our slides to get the next question. Now this one's really kind of hard to read. You may notice that the 0.2 looks like it's at 1100 for the value in dollars. But in this case, they are not asked to write an equation for this function, so technically they won't need that. They'll just need to estimate some of the values that they're asked about. So there are three questions. It asks for f of 0. What does it mean in this situation? And they'll just use the labels on the graph to answer the question. What is f of 4.5? And what value of t is going to give f of t is equal to 1500? What does it mean? This 4.5, when they do that one, they're going to have to estimate about what that is because there is no line at that spot. So just tell them get as close as you think you need to and then answer the question. The third scenario is about the cats, and I do tell them just answer the first three because it does ask them to graph it on here. And since we don't use that particular calculator that often, kids tend to be a little frustrated when they try to graph it in there. I'm not opposed to them doing every question on the screen, but I'm not going to make it mandatory. So you could say it's optional. If you want to do the graph, you can. They're going to answer these questions. What is the value of f of t when t is 0? So it's a different way of asking for the y-intercept of the graph. What is the approximate value of f of t when t is a half? And what does that mean in this situation? What does the number 1/3 tell you about the stray cat population? Next, we will go to the Desmos activity and we will work with applications of functions. There are 17 screens. So I would say that what you've seen so far should be at least half of a class period, if not longer. And you do want to leave plenty of time for students to create their own at the end. So 1 to 2 days is recommended for this lesson. So let's start with the first screen. Now this time I've given them equations and they need to pick the one that fits this scenario the best. The reason I did the slides talking about the growth rate and the percent growth, there's just a difference there. So the growth factor is not the same as the percent growth in these problems. So they need to kind of pick those apart. For example, this first answer choice is actually 240%. It's not 2.4%. So that's a lot. And 240%, if you look at that, you're going to take out 100%. So the growth rate is actually 140%. So that's a really tricky one. I have given them the graphing calculator in this assignment, and I do encourage them to type these in and look at the numbers if necessary, because we want to make sense of what these equations are doing. And then obviously this last answer choice is a linear function. Well, this is a percent rate of increase. That means it's going to change each day. It's not going to give them the same number of termites each day. It's based on the new number each day. So anyway, have them examine these closely. Please encourage them to use the graphing calculator until they've really mastered this concept and know it well. I do expect them to look at these graphs, to create tables, whatever it takes to really make sense of the growth rates in these percent growth rate questions. Now we're doing the exact same scenario, but this time we're talking about a decay. So the homeowner is got a new remedy, and this time the number of termites will decrease 2.4% per day. We call this exponential decay. So what is the decay factor? So what is being multiplied here? Now once you've had these conversations, I would open these up one screen at a time and have conversations before they move on, so that we know that they know where these numbers are coming from. So in problem 2, we have Juan buying a gaming computer for $2,100. Wow. Juan must have a lot of money because that is an expensive computer. But the value of this computer is a function of time and year, and it is decreasing 45% annually. And you may want to discuss that word, because we are going to be using the words annually and yearly in test questions from here on. So if students don't know the word annually, right now would be a good time to kind of add that to your word wall or discuss it as a class. Problem number 3, we now have a substance that is decaying. So this is a percent decay. Once again, we always start at 100% and then decrease from there to figure out our multiplier. The word multiplier, growth factor, decay factor are all the same. Once again, we have a growth problem. She starts with 300 stores in the year 1999, and the number of stores is a function of the number of years. Since she started in 1999, that would be year 0. So what year would the year 2007 be? So you may need to stop and pause on this one. Creating tables is a great way to keep track of the data and then to come up with an equation to represent that data. Now once they get past screen number 5, we're going to get into the stuff we did last time. So this is sort of a review. What's the same about these graphs and what is different? Now you can click on these and you'll notice that all the graphs intersect 0, 1. But if you drag along this graph, I can get to one. Oh, it's right here, my bad. Anyway, we're going to write down one thing that is the same and one thing that is different. Of course, you could say a lot of things. These are all continuous graphs. They're all increasing. They're all going through the point 0, 1. None of these graphs touch the x-axis. We're going to get into that more in this lesson. Okay, this is the first time we've introduced the term asymptote. Weird word, hard to say. They usually go, what? When I introduce it. But this is an asymptote. It's actually dashed red down here. And we call this a boundary line for our exponential function. The function gets really close to that line, but it doesn't intersect it. And then I ask them to tell me why. Why can't the graph of y equals 2 to the x intersect the line y is equal to 0? Let's go backwards on this graph. If you go backwards on the graph, you're taking half. So you start at 2, and let's go backwards 1 will be 1. So I'll say, come stand next to this wall and be 2 feet away. Now 1 foot away. Now half foot. Now a fourth foot. Now, yeah, you'll get so close to the wall that you can't move anymore, but you can't get to 0 because I'm going to continue to call out numbers indefinitely and never get to 0. So that's a physical representation of the asymptote. If you need to do something like that as a brain break, that would be kind of a fun activity. Now they're going to transform the graph, and they're going to use these drawing tools to do it. So just plot 3 points that satisfy this condition. What if we graph y is equal to 2 to the x plus 5? How does that compare? So here we have 2 to the x already graphed in blue, and they can use blue or they can change it to some other color. Like if they want to do green, that's fine. So this crosses at 0, 1, but if I move it up 5, where's it going to cross? And then this is at 1, 1, 2, which is here. But if I move that up 5, where's that going to cross? This is at 2, 4. But if I move that up 5, where's that going to cross? Now that one I don't think is going to show, so you might want to come over here and pick the point at -1 and choose that one to move up 5. Once they've moved everything up, they can connect the dots. They can even draw themselves another asymptote. So they could use maybe the red one and make it real thin and then erase to make little dashes. That's how I make dashed lines. This is a review of the last one. It tells you to change one number to make it work. So I'm not going to tell them how, but hopefully they already know from the last lesson. They're going to do this one as well. And then this one, they're going to enter one equation to collect all the stars. So we'll just let them play with that. Now here's where it gets a little interesting. They're going to type in a linear regression equation. So that is y1 tilde mx1 plus b. So we're reviewing our regression equations that we do need to know for our test, which is next class period. Then they're going to type in a new one. This is an exponential regression. y1 tilde a times b raised to the x1 power. They type it exactly like it's there. They don't need to cut and paste it though. They need to actually type it in. And is this a good fit? And then you can also have it translate the graph up, which by the way they do need to do on this particular problem. So y1 tilde a times b raised to the x1 and then plus c. And it will automatically translate the graph. And now between the three, they need to choose the one that did the best. Which one connected the points the best? One of them is actually a perfect fit. So they'll need to explain their thinking after each one, or for the one that they chose. Now they're going to practice by sliding this around. You see how they... So we'll start with k as 1, and then they'll slide it around. They'll slide this around. That makes it steeper. And then they'll move it up. So their goal is to get this done. If they need the asymptote, they can click here. That is a boundary line that it cannot cross. So if they're struggling, tell them to look at that. Some of the kids are automatically going to think, wait a minute, I could make a regression equation for this. And you know what? They absolutely can. So that's kind of the intent of me showing them that first. If they're struggling to find the values, then they can find them via that. Here's another one. They're going to try to match it up. They want this blue to land straight on top of that black one. And they're going to move these around to make that happen. And then the last thing they're going to do is create their own growth function. Now they need to know that the growth function has a multiplier greater than 1. So I would definitely go group to group and check your kids' functions. If you see a kid giving you a growth factor not greater than 1, then you will know something's wrong. And you may have some kids try to create a linear function. So that's another thing to check on and have your kids talk about that as a team. Are all your functions exponential? And then finally, they're going to create their own decay function. They are creating a table, a graph, and an equation. How many points are in their table? Doesn't matter. They can have as many as they want. I sometimes tell the kids don't count by ones in these tables because, unfortunately, depending on your function, you may not be able to tell it's growing that much if you have a really big number or a really small growth factor. So it depends on the student. But I tell them if you don't see an obvious curve to your graph, consider making these numbers more or changing them so that you can really see that curve. And that concludes our exponential applications lesson. Our next class period will be our last regular test of the semester. Y'all have a great day.